I would like to invite another author, Mr. Smiley, who will present fatigue crack propagation initiated at artificially made small defect in two different heat affected zone microstructures. Please.
Thank you, Chairman, for the presentation. Hello, everyone. Our story is also related with fatigue and in welding joint. So, the content of our research story is shown in the slide. We are focused in heat affected zone because it is really very complex and heterogeneous, and also it's harder to test. Only a few methods are able to test, like hardness, hardness. But before moving forward, we have to explain that the load carrying capacity of the entire weld joint usually depends from the weakest part of the joint. It's like a chain. If we load in the two different directions, it will fail on the weakest part of the chain. The material as a delivered condition is nickel molybdenum alloy steel, and mechanical properties and metallurgical data are shown in the table below. We are actually, if we refer to CCT diagram, we belong in this region. Or specimens have microstructure with martensite and some bainite. So, as I mentioned before, heat affected zone is hard to test. Only the bigger hardness can be tested because it is very narrow in real weld, and our idea was how to prepare specimens in order to describe the entire specimen. So if we know the cycles of thermal cycles of heat affected zone, we know that it is divided in sub-zones, like coarse grain heat affected zone, fine grain, intercritical, and over temperate heat affected zone. And our focus was in coarse grain and fine grain. We have prepared specimens in such condition in order to test, to make different tests, such as the tensile test, Sharpie, and fatigue also. This is about the heat transfer in 2D and 3D during the welding. Equation to calculate in which region we are. This is for 2D heat flow and 3D heat flow transfer. This cycle, this is the thermal cycle which we have prepared which we get from the welding simulator. We know that I already described here is coarse grain nearly the weld metal, and this is the diagram which we get from the welding simulator. How does it work? I have put one video in order to explain this. Here are the thermocouples which are attached in the specimen. Now the condition from preheating are starting. Here is also dilatometer which calculate transformation of I don't know why the video is not running. It's not now it's running. Yeah. Here below is the dilatometer, which measure the transformation of the microstructure. As I mentioned earlier, now the preheating conditions are starting, and peak temperature now it's the peak temperature is arrived, and after this cooling down. This thermal cycle make coarse grain heat effective zone of the material. Another possibility to create a coarse grain heat effective zone in wider zone is laboratory furnace. Here is shown also the thermal cycle which we used. Preheating till 1100 temperature, then coarse graining, and cooling in furnace till temperature will achieve 870, and after that cooling water quenching. This is about the fine grain heat effective zone preparation. And the microstructure which we achieve. These are coarse grain which we have measured. The average grain of was 200 microns, and if we compare with fine grain, it is 10. The average of grains was 10 microns, which is quite big difference. Now we will spoke about the tensile test. In the first diagram is shown the base material tensile test, coarse grain, and the fine grain heat effective zone. So we have prepared tensile test in wider tensile specimens in the wide, which describe also the each of subzones which we have in heat effective zone. The results of instrumented Sharpie test and the scanning electron microscopy of both breakage of specimens. This is about the decline roll. The load ratio was 0.1, and we saw that according to Paris curve and after evaluation of the results, we got that the threshold for the coarse grain heat effective zone is 10.7, and for fine grain is 4.3, which is also quite big difference. And this is the defect which we made, artificially defect which we made in both microstructures. It is a Vickers indentation. In first case, where grain was bigger than the size of defect, and practically it is microstructurally small crack. So while the crack begin and propagate till achieve the border of the grains, and after that it's one barrier which doesn't allow to move forward. In the second case, we have fine grain heat effective zone where Vickers indentation or artificial defect is bigger than 2 or 3 grains, and so while the grain boundary is smaller to resist the crack propagation. cracked welding joint, we have stress concentration, KT 1.74. These are the specimens which we tested, and yeah, somewhere here we have put the defect which I already described. This is about Wheeler curves. We got the Wheeler curve, and this is about microstructure and breakage. We have breakage at 800 megapascal and 1,360,000 cycles. Endurance limit for the coarse grain specimens was 760 megapascal, and the endurance for non-breakage specimens have survived only under the 664 megapascal. This is about the fine grain heat affected zone. We have evaluated the endurance limit, and the endurance limit of the fine grain heat affected zone was 525 megapascal. So the crack has propagated in the diagonals of the indentation, and this is about the microstructure of breaking specimens. So a couple of conclusions could be right. At first, we have solved that coarse grain heat affected zone has larger threshold for the long crack propagation in comparison with the fine grain. It is about 2.5. Some small cracks which have been initiated stop it to propagate in coarse grain as a result of grain boundary resistance. But in fine grain, they propagate without stopping because the grain boundary is weak and doesn't represent a strong barrier to stop the crack propagation. At the beginning, the longer crack growth is faster in fine grain heat affected zone microstructure than in coarse grain heat affected zone. When the crack overcame the microstructural barriers, it in coarse grain crack propagation propagate really faster in the coarse grain heat affected zone. And we have to say also that the toughness of fine grain is larger than in coarse grain. So.
Thank you.